Okay, so I wanted to entertain you today about Bitcoin, and wanted to explore whether this is really a disrupting technology or it is a mafia haven. So we'll try to answer those questions today. But I want to be clear, this is not an investment lecture, right? So in my opinion, Bitcoin does not produce any value, goods, or cash flow. It's really about speculation, but by that I mean that you hope that the next person will pay more than you. My goal is more to raise awareness about the security and the blockchain, the blockchain technology applications. Because yeah, you know Bitcoin, and it's about money, but behind blockchain there is a lot of possible applications that are very, very interesting. So we'll cover the crypto primitives, what is a blockchain, how the decentralized consensus works, Bitcoin, what is actually Bitcoin mining, and we'll cover the main features, limitation, and costs over other systems like Visa and PayPal. We'll talk about Bitcoin attacks and some controversies, other application of blockchain and disrupting technology, and some further readings. So it all started in 2009 when a man, well, we suppose this is a man, we don't know who that is, but the name on the paper is Satoshi Nakamoto, and there's a lot of speculation on who that person is. To this day, I've I know there are like 3-4 persons possible, but they don't know. So Bitcoin is permissionless and borderless. It's easy to send and receive money anywhere in the world, a little bit like PayPal or QuickPay. It does not require an ID, so your identity is hidden behind a pseudonym. We will talk about that later. It is censorship resistant, so in theory, a country cannot censor the use of Bitcoin. It is decentralized, so there's no need of intermediary, and there is no central server or central controlling entity. There's almost no fees and no storage costs, but you'll see that there is cost in the power consumption. There's no single point of failure, so a node can fail and the other nodes can perfectly work together without that node. But there is a limited supply of Bitcoin. You'll see it's limited to 21 million Bitcoin, and that's one of the limitations of this blockchain technology. So there are many other blockchain technology, but this is one of I mean, this is the first one and probably the most interesting to study. Okay, so we need to explain a little bit some of the cryptographic primitives that are used, and the first one is a hash. So a hash takes an input, typically large, and digests it into a fixed size output, and that we typically call the fingerprint. So you take initial vector, and then you add different block of messages, and then finally it produces one fingerprint, which is, for example, for SHA-256, it's 256 bits. It is easy to compute the hash, but it's hard to reverse. So a few security properties. First, it's one way. Okay, so it's given the hash to the output, it is infeasible to determine what the input is. It's collision resistant, so it should be infeasible to find two inputs, A and B, such that the hash of A is equal to the hash of B. And it's puzzle friendly. So this is very important because this is the base for mining. I'll explain a little bit here, but I'll explain a little bit better what that is in a few slides. But essentially, if you decide on a puzzle ID and so a random value X that you can change, you can determine what you can fix what the output could be by fixing, for example, that a certain number of MSBs of Y of the output are zeros. Okay, we will talk more about that in a few slides. Yeah, SHA-256 is used in Bitcoin. That's the most important. Okay, the second important primitive is public key and digital signature. And I apologize if most of you know already how that works, but I think it's important to understand the basics. So it means that all entities must generate a key pair, which consists of a secret key and a public key, such that the public key is equal to the secret key multiplied by some generator point. And the multiplication here is not just a straight multiplication like you probably used to. It's a special operation, okay? Over a Galois field or binary field, for example, if we use elliptic curve. And it starts from a generator point that allows to generate a full cyclic group. It should be virtually impossible, and that's called the discrete logarithm problem, to compute the private key from the public key. So if you have the public key and the generator point, which is also public, you should be able to compute the private key, because this operation here is not easily reversible. It's not. That's why it's called discrete logarithm problem. Okay, so how does a signature work? If Alice uses its private key to sign a message she wants to send to Bob, then Bob can verify that signature with Alice's public key. So Alice shares her public key with Bob, and then she will append a signature. We use a primitive called sign that uses Alice's private key and signs the message, and appends that signature to the message, and she sends both to Bob. Then Bob can easily verify that this signature is valid and was correctly generated with the secret key associated with Alice's public key. So this proves that Alice has actually written this message and signed this message. Feel free to stop me if you have any questions. I may stop here just to see if there's any question about hash and public key. Okay, hopefully that's clear. So in Bitcoin, the public key here is called an address. Essentially, it's the same as your bank account. So in the same idea, your bank account can be, your bank account number, sorry, could be your pseudonym, right? It doesn't say who you are, but it is yours, and it is uniquely identifiable. Okay, so now we jump to Bitcoin. The fundamental building block of Bitcoin is, of course, a coin, right? It is a currency. A coin is characterized by a unique ID, a quantity, or which is an arbitrary number with 8 decimal places, and an owner. The owner is typically pointing at the address, or what do we say, the public key associated with you. The coins can be split and merged, and if Alice wants to send Bitcoins to Bob, she will merge some of her coins and then split the result between her and Bob. Okay, so she wants to send some 3.5 Bitcoin to Bob. She has to merge 2 and 3 together to form 5, and then she sends 3.5 Bitcoin to Bob, and then she sends back to her 1.5 Bitcoin. Okay. So what are the components, the very important components of Bitcoin? So it has a transaction structure. So we will see a bit more the detail of how a transaction looks like and how it is organized into a blockchain or append-only ledger. So in a blockchain, essentially, and this is the most important, if you have to remember one thing, is that you have a public ledger to which you can append a series of transactions in a unique way, and that cannot be changed after it has been added. So you cannot you cannot reverse if you made a mistake. For example, you send something to Bob, and you send too much. You send $1,000 instead of $500. You cannot change that, but you have to contact Bob, and Bob has to reissue a refund, which is a new transaction that would be added in the ledger after that. But the ledger itself is not cannot be changed. Then you need a peer-to-peer network for propagating, verifying, and storing all the transaction data. So this peer-to-peer network is constituted of a lot of nodes, or that and all nodes or most of the nodes are also mining, as we're going to see. Then between all these nodes, it requires to have a distributed consensus system. And in Bitcoin, the way we obtain consensus is by using proof of work. So all the nodes will compete to prove they have been able to generate the next block that will be added to the blockchain. And the first one that finds it is the one that will get rewarded. But we will see that in more detail very soon. So the Bitcoin system components are one blockchain, a peer-to-peer network, and a distributed consensus, which is executed by all the miners. And usually all the nodes in the peer-to-peer network are also the miners. Any questions so far? Okay. And then you have all the users, like you and I, who have a wallet. And typically you can use Coinbase, the very common wallet to exchange Bitcoin and other blockchain currencies. And those are connected to the peer-to-peer network, but they are not mining. They are simply users. Okay, so what is a blockchain? And we have seen what a hash is. So now we'll see what a hash pointer is. The data structure with, so a hash pointer is a data structure with a pointer to the data and a hash of the data. Okay. Blockchain is a linked list with hash pointers and pointers. The use cases are typically temporary log or a pen-only ledger, which is exactly what we want to do in Bitcoin. So let's say we have the genesis of Bitcoin here, and Satoshi Nakamoto generated the first block. So what he did is he generated a few transactions. Then he collected that into this data 0, and then hash here. There's no previous transaction. So the block 0 is the whole data 0, and hash he has the block 0. Then there was a next, whoops, sorry, I went a bit fast. There's a next block created after that, where they created more transactions. And that data 1 here, where the transactions are, were merged together with the hash of the previous block. And then this miner would create the hash of block 0 and the data 1. So you can see that with the hash of block 1, nobody can change or modify anything in data 0 and data 1 without anyone be able to verify that this is actually wrong, that the data is not correct. Right, so the hash of the block 1, which is a fingerprint of the whole data 1 and hash of block 0, allows anyone to recompute the hash of the block 1 and verify that nothing has been moved. And that nothing has been modified. Same if you take the block 1, the hash of block 0, you can verify that nothing has been modified in data 0, etc. Right, so and so on. Every time you add one block in the blockchain, you move one position, and you calculate what the hash is. So that's what we call a hash pointer. So that's blockchain, guys. That's a blockchain technology. There's nothing more complex to it than that. So in terms of the structure, of course, we need to have distributed consensus, and we will see how to achieve that with miners in a couple of slides. Okay, so it's, if you're interested, the data one, so the transactions are not simply listed in data one, and the hash is executed on the whole block. Actually, they use a more efficient way to represent all the transactions. That's called Merkle tree, where all the leaves of that tree are the transaction, and then what they put into the hash of the block one or hash of block two, actually the root, the hash root of that tree. Okay, that's very useful because if you need to add large hash pointer structure, then the proof of any member is in log n of that tree. Okay, so Bitcoin, now let's talk about the transaction-based ledger. So Bitcoin uses a transaction-based ledger and not an account-based ledger. So you might be familiar with an account-based ledger where you just record what has been transferred and what has been credited to the different people. So, but if we look at this last transfer here, transfer of 15 coins from Alice to David, how do we know it's valid? The problem with that is we might have to scan backwards until the genesis to know that it is valid. Because how do we know that Alice actually has 15 coins in her wallet? How we can prove? Remember that this whole ledger is public, so anybody can verify that this is correct. So actually, Bitcoin, like I said, uses a transaction-based ledger. So what it is, it records the transactions with very specific rules, exactly like it is shown here, where you have the inputs and the outputs. And the inputs are always fully consumed to generate the outputs. And if a transaction uses the output of a previous transaction, it has to fully consume all the output of that transaction. So let's see how that works. For example, here the input is the zero index of the second transaction. This is the second transaction. This is the index 0. This is the index 1. Okay, so that would be the index 1 here, where Alice has 8 Bitcoin, and we'll split that between David and herself. Okay, so and it's very easy to verify, to know that the transaction is valid, because if a transaction was already referenced in a previous transaction, then it's invalid. For example, in this transaction here, assuming that this comes here after transaction number 4, the inputs 2.0 or 2.0 was already consumed in transaction number 3. So it's very easy for a node to scan quickly this and to see, oh no, 2.0 was already used, so this transaction is invalid. I'm going to reject that. Okay, like I was saying, Bitcoin, the entirety of a transaction output must be consumed by another transaction or none of it. Okay, so the entirety of an output is, for example, here, the 17 Bitcoin that were going to Bob is completely consumed by the transaction number 2, and Bob decides to pay Carol 8 Bitcoin and to keep 9 Bitcoin. So this would be the new value output for Bob to spend money. Okay. For details, that's really interesting, but I think that those are ideas that I found they were pretty cool. Okay, so what constitutes a valid Bitcoin transaction? So we talk about what we just discussed, but then inputs are unspent outputs of previous transactions. We just mentioned that. The total coins in is smaller or equal to the total coins out. You'll see why, because you might want to have voluntary transaction fees. You may have heard that Bitcoin, you have transaction fees which is the coins in minus the coins out. Okay. This is important, and you will see why again in a few slides. If you want to look at all the rules that are forming a Bitcoin transaction, please refer to this link here. But I think it's a bit too much for this presentation. Also, I didn't have the time to cover Bitcoin scripting, but Bitcoin has a scripting language that can do a few things, and that's a little bit that gives the idea of the different blockchain like Ethereum that are specialized in smart contracts. So essentially, you can record a script that will execute something, so like a contract, like pay to script or proof of burn, that can allow you to do certain things like a transfer of a deed or a transfer of a title, something like that. Okay, I just put some example of transaction here. I encourage you to consult them if you're interested. This is, for example, a coin creation when a miner actually receives a reward, and you see that there's a genesis creation of a coin, or simply another transaction, normal transaction that was recorded here. Okay, so now it's time to talk a little bit about decentralization, which is at the heart of Bitcoin. Remember, you have to know that not all blockchain require that you have decentralization. Right? You can completely have one bank deciding to use blockchain technology between different services so that it smooths the interaction between different systems. So maybe you have a system for accounting, a system for international transfer or whatever. So it allows blockchain allow that bank to implement a system that would be a bit easier to go across platforms and across different systems in their system. So, but Bitcoin is decentralized. So some example of decentralized system is the internet or your email with the SMTP protocol. Some example of centralized systems are Facebook or fiat currencies. So fiat currencies are currencies you and I use every day, like the dollar or any other currency that is running in your country. But how to obtain this decentralized consensus? So that's the second biggest idea of Bitcoin. So it needs to use a distributed consensus protocol. Let's say you have n nodes, and those are the miners, that each have an input value. Some of these nodes are faulty or malicious, and you don't know how many. Right? So some of the nodes, some of the miners will try to cheat. So distributed consensus protocol has the following two properties. It must terminate with all honest nodes in agreement on the value. And the value must have been generated by a honest node. So what is the algorithm? The first thing is that new transactions, so users like you and I, will need to exchange money, right? So every time we send money or receive money, there's a new transaction that is issued, and all of these transactions must be broadcasted to all nodes, to all the miners. Okay, so each node or each miner will collect these transactions into a block. We've talked about the block earlier when I explained what a blockchain is. You create a block and you hash that block, and that's what creates the next block. In each round, a random node gets to broadcast its block. So Bitcoin will add a new block every 10 minutes. And we will select randomly one of the miner, and you will see how we obtain this randomness or random selection. Within 10 minutes, we need to select randomly a node, And then this node will add in block to the blockchain, and then broadcast is blocked to all other nodes. So the other nodes accept the block only if all transactions in it are valid. So we talk about what makes transaction valid. It needs to have valid signature. It needs to they cannot be double transactions. The nodes express their acceptance of the block by including its hash in the next block they create. So, every 10 minutes in Bitcoin, there will be a block of transaction that is added to the ledger. And all the block within those 10 minutes, all the nodes are competing to try to find the next block. And then the first one that finds the next block will include that block and broadcast immediately to all other nodes. And all nodes, if they're honest and they see that this is a valid block, so if all the transactions in it are valid, and you will see that if the puzzle was correctly solved, then they will start computing the next block and include that block into the chain. And that's exactly what they do here, the fifth step. Okay? So honest node behavior is always to extend the longest valid branch that they see, because you can imagine that those blocks, so you might have two nodes that have found a block at the same time, right? Or maybe there's a node that's trying to cheat and attempt to make a double spending of some amount of money. So the way all the honest nodes will select what is the correct transaction here, that is CA transferred to B or CA transferred to A prime. Actually, what they do is they always select the longest branch with, of course, valid transactions. So all these steps must be correct. Now I'll pause for a minute just to see if there are questions. I don't know if that's clear.
No, can you please explain if there are more malicious nodes than the honest nodes? So what will happen in this situation?
Yes, it needs to. You need for the whole system to work. You need to have at least 51% of honest node. So a little bit. You need to have a majority of honest node. Otherwise, yes, if you have nodes are colluding and with each other and to form a majority, then they can be dishonest. But the whole system would quickly collapse if it was the case, because the users would not trust the system anymore. But yes, it can happen.
Right, thanks.
Any other questions? Okay. So how do we select randomly a node to generate the next block? So remember, all of these nodes in that peer-to-peer network, all of the nodes are competing, right? So how do we pick randomly the node to generate the next block so that at least 50% of the time we pick a honest node? And how to provide incentives to nodes for behaving honestly? The solution is to run a lottery where winners get a reward. So that's why we call it Bitcoin mining, because they do a work, which is why we call it proof of work. So basically, they calculate the hash, and they need to spend resources. So they need to, like at the beginning, it was simple computers. They were running a hash, trying to find a solution to the puzzle. And then, of course, this became more evolved with really Bitcoin farms. We will see some pictures later. But this lottery is really what we call the mining, and the reward is some Bitcoin. So some Bitcoin is injected into the system. So there are other methods than proof of work, and I'll just mention one, which is proof of stake. I'll encourage you to read more about that if you're interested, but this is I don't have enough time to explain that as well. Oops, sorry. Yeah, there are other possible interesting readings about Sybil attack on peer-to-peer network or double spend attack, but once again, I don't have a lot of time to cover that. Okay, so how does the lottery works? Well, remember you need to compute a hash with all the transactions you are aware of. So let's say all the users, they create transactions, and they will broadcast these transactions to all the nodes in the peer-to-peer network. Okay, so the nodes will receive a lot of transactions and will select a certain number of transactions to include in the next block. And maybe they won't select all the transactions and look at all the nodes separately. They may not have and receive the same transactions, but that doesn't matter because at some point they will receive those transactions and can add them, right? If they were not already added in the previous block. So let's say this is one node here, and that node receives, let's say, 200 transactions that it is aware of, and we'll add those transactions. We'll add the previous hash, which is the hash pointer to the previous block, and they will add a nonce. So a nonce is a random number that it has to be used once. Okay, hash everything, and let's say this hash has to be smaller than a certain target. It is also called the complexity in Bitcoin. So what is that target? Remember, the output of this hash is 256 bits. Well, what the complexity of the target is to say that we won't force the leading zeros at the output to be, to force the MSB or n MSB to be 0. And the number of zeros is actually the target or the complexity, right? So you can easily imagine if hash is a good oracle function, then the output is random or looks like random. So you generate a nonce, you calculate the hash, and then you look at the output. Does the output have n zeros or not? If it doesn't, then you change the nonce and you compute again. And then you check again, and if it has the n zeros, then you're the winner, right? You have found one solution to the puzzle. And all the nodes in that peer-to-peer network that we have seen, all the miners, that's exactly what they do. So that's why maybe you've heard or seen that they are creating a very efficient way to hash so that they can hash as fast as possible and compute. So what they have is they really have farms of servers computing hashes, and only that, and to be the first to find that that solution to the puzzle. Okay. The target or difficulty or complexity is adjusted every 2.6 days. Originally, it was every 2 weeks, and it's a function of how much hashing power has been deployed. So you can imagine at the beginning, people were doing, or hobbyists were doing that with some Raspberry Pi in their garage. But then quickly it evolved into more advanced solution with using GPUs or FPGAs and then ASICs. And then they organized themselves into farms. And I'll show you a picture of that so that they get more hashing power and they could compute more. They could try more nonce in parallel so that they're the first to find the solution to the puzzle. And of course, if they're the first, then they get the reward, they get the Bitcoin. So you can understand this is a lottery because if you look at all the miners, the probability of a node or a miner winning the next block is a fraction of the global hash power it controls because you cannot predict what the output is given the input, right? with a good cryptographic hash function. So you have to try different random value with this nonce and try again and again until you find a solution. And it is calculated every 2.6 days how much zeros you need here so that a new block is generated every 10 minutes on average. Okay, so this is really the key idea of mining, and I hope it's clear. If you have any questions, don't hesitate to ask.
Eric, what's the maximum amount of complexity that's been used, I guess, so far in this algorithm? Do you know?
Not on top of my heart. Sorry, not on top of my head, but maybe in the range of 40 bits. I mean, if you type Bitcoin charts, you'll find this is completely public knowledge. And if we have time, we will look it together at the end of this presentation, Kurt.
Okay, cool. Thank you.
Okay. It is, of course, trivial to verify that this is a solution to the puzzle by all order nodes. So all order nodes, once they receive the block and the hash, and here the hash of the block, they can easily verify, okay, if all these transactions are valid, this is a pointer to the previous hash, and with this nonce, the solution has n zeros. Okay, so this is very easy for all the nodes. So as soon as the other nodes, if they behave honestly, as soon as they see a solution being sent to them, they will stop trying with the previous node. They will take this new hash as previous hash, take all the transactions that are not in this hash that they are aware of. So of course they will not try to include the transactions that were in the previous in the hash that was previously calculated, right? So they will have to remove that and restart trying to find a solution to the puzzle for the next block. Okay, what are the rewards? So the rewards for the miners is Bitcoins, okay? And that's why there's a maximum number of Bitcoins, which is 21 million. And at the beginning, the reward was 50 Bitcoin per block, valid block you find or a miner finds. And then in 2013, there was the first inflection point where they changed that. So they have the Bitcoin reward every 4 years. Okay. And then at the end, they will not inject any more Bitcoins. So what happens in the end if actually there's no more reward? Well, actually, there's another tool that the users can use. It's the transaction fee, like a tip that you provide to the miners to include your transaction into the Bitcoin. So you can imagine if you give a good tip, well, then a miner will be will have an incentive to include your transaction sooner. So if you're not in a hurry, then you don't have to pay a transaction fee as high as if you're more in a hurry to see your transaction being validated and included in the public ledger. Okay, so we are very close to the next inflection point here on May 2020. We will halve again, and we will get about 6 Bitcoin for a block that is solved. So I wanted to show you what a block look like. You can see the hash contains a certain number of zeros, and this is hexadecimal. Okay, so that is once again the number of zeros here of the hash of this block here. And the number of zeros is the complexity. So only that part here is actually hashed during the mining, right? So if the miners, they have to hash all the transactions, that's a lot of hashes. So what they do usually, they assemble the transaction into a Merkle tree, and they include the Merkle root in the part that they will actually hash, and that is perfectly valid, right? Because it's if somebody changes something in one transaction, that will change the Merkle root, and that will be detected. So you can see that the nonce is here. That's the nonce that this miner has randomly picked, and thanks to that, he has found one solution to the puzzle, right, with leading zeros. Well, I made a small mistake here. The hash itself is not hashed during the mining, right? So it starts a chain, and the hash is the solution of all these fields or structure here and content that is hash. The transaction ID dot hash. Sorry, that may be a bit misleading. It is hash and collected into the Merkle tree root, but it's not hashed during the mining. Okay, these are the mining puzzle information. And once again, if we look at our hash chain of blocks that we discussed that form the blockchain, there's all the transaction hash with the Merkle tree here, where you have all the transaction, and you hash this part, so which is exactly this part here. Hope you can follow my pointer. Okay, the transaction hash is here. The previous transaction hash is here. You can see again the leading zeros. And if you want to know more information, there's a good link that you can consult. Okay, we discussed that. So let's see how we're doing with time. Okay, I think we have covered this, but essentially a node, like I said, a node is associated with a miner. So a node collects all the transaction into a memory pool and include all those transactions in the transaction list of the next block it calculates. Once it has found a solution, it will update the blockchain and broadcast. So Bitcoin features and limitations. So the size. Node must store the entire blockchain, and that is currently today about 263 gigabytes of data. That's the entire blockchain. Okay, but and this is more about limitation. If the whole world was using Bitcoin and only Bitcoin for all the transactions, it would add 350 gigabytes per day to the blockchain. So I wanted to emphasize here that the limitation Bitcoin in terms of, okay, if everyone uses Bitcoin for everything, for all the transactions, that would be unfeasible. Very quickly, all the nodes would have an amount of data that would be unmanageable. And second limitation is throughput. So this is also defined in Bitcoin, and some other blockchain have tried to solve that. But in Bitcoin, this is the rule, you have 1 megabyte per block every 10 minutes. And it's about 250 bytes per transaction. So that means that you have a maximum of 2,200 transactions per block, or 2,200 transactions every 10 minutes. So on average, it's 3 transactions per second, with a max possible of 7 transactions per second. If we compare that to Visa or PayPal, I mean, you can see the Visa is about 1.7 kilo transaction per second, with a peak around Thanksgiving and the Black Friday for about 56 kilo transaction per second. The cost or the transaction, the cost per transaction. So those are the fees that you want to pay. And remember, I told you that the more you pay in a transaction, so the higher the tip you give to the node or the miner, the more chance you'll see your transaction including in the next block. You can easily imagine that if there is 5,000 transactions issued, then not all transactions can make it into the next block, because there is a maximum of about 2,200 transactions per block. So the current price as of today to have your transaction included in the next block is about $0.4, so 40 cents. But if you're willing to wait a little, so if you, that's what we call the 6-block fee. So if you're willing to say your transaction will be included in one of the 6 next block, then it's about 0.24. In comparison with PayPal or Visa, that charge typically 2% to the vendor per transaction. Latency, that's also a limitation of blockchain. So a block is confirmed to be part of the blockchain when at least 6 blocks have added on top of it. So essentially, it takes an hour to confirm a transaction, and that's also clearly a limitation. Okay. Okay, that part is to me a bit the most shocking part is the cost and environmental impact. So the evolution of Bitcoin mining, and I mentioned that earlier, beginning was using CPU or small Raspberry Pi, and people switched to GPU to be more efficient, FPGA, and Bitcoin farm, for example, in Iceland where it's cold, you can see that they have racks and racks of ASICs just hashing and trying to find the next hash. So the issue, of course, is that we have seen with these Bitcoin farms a consolidation. So it's more centralized than it was at the beginning, which is also not exactly what was intended at the beginning. Is to because if someone controls 51%, then they can cheat easily. So I wanted to put some stuff in perspective here. The cost of running Bitcoin, all this electricity needed to calculate the hash correspond to 77.2 terawatt hour per year. That's about the electricity consumption of a country like Chile, and it costs about $3.4 billion. Okay. So that's not a small number. Of course, you could argue that even running the USD, the US dollar, also costs a lot of money. But to me, that's really a lot of money, and that's why I think some alternative to Bitcoin that uses, for example, proof of stake instead of proof of work could be really more advantageous in terms of efficiency and cost. So just put things in perspective again, each Bitcoin transaction requires the same energy as 770 kilo Visa transaction. And the carbon footprint per transaction is 308 kilo CO2, which is about 35 gallons of fuel, if I calculated this right. Okay. Okay, what are the cryptographic limits in Bitcoin? So Bitcoin uses the elliptic curve digital signature algorithm with P256. So there's one signature algorithm, and they have hard-coded in their code a hash function, so they cannot change a hash function because you have to be able to calculate what is the hash of all previous blocks if you need to verify the transaction. So that cannot change easily. And those crypto primitives might break, especially the signature algorithm, by 2040 or sooner if the quantum computer becomes a reality sooner. And I think the previous talk was exactly about that. Although there's no proof that you can generate enough qubits that are error-free to break ECDSA today. So you need enough qubits, but you need also enough qubits that are error-free, or you need a lot more qubits that are not error-free, and that's, people don't think we're going to be able to break ECDSA, so the elliptic curve, the discrete logarithm problem, before 2040. But this is really a guessing here, so we never know. So what is the future of Bitcoin? What if they have to change these algorithms? Well, to solve those deficiencies that we have seen, like, we can generate a block every 10 minutes, etc., or maybe we need to change the signature algorithm, we can do a soft fork or a hard fork. And one of the first soft fork was Bitcoin Cash. So, and their goal was to reduce the transaction times. So, but you have a lot of other hard fork or soft fork from Bitcoin, that have emerged with the years. So Bitcoin could be replaced by some competition cryptocurrencies, and just to cite here a few of them, like there's Ethereum, Litecoin, Ripple. Today, I think this number is not correct. It seems that those are not my latest slides. I apologize, but Kurt, you have my latest slides. But there's about 5 existing blockchain or cryptocurrencies today, that it is today, with different goals. So in the title of my presentation, I'm looking at time. We're really short in time. So I'll move quickly through the slide here. But can Bitcoin be a money laundering tool? I don't think so, because essentially Bitcoin, you always have a pseudonym associated with your Bitcoin, and the pseudonym is not, you cannot be anonymous completely with a pseudonym. To really obtain anonymity, you need pseudonymity and unlinkability. So meaning the different interaction of the same user with the system should not be linkable to each other. For example, with respect to places or patterns of interactions, like you bought some stuff here and there, but anyway. So anonymity and decentralization that requires traceability are really in conflict. But the real problem, in my opinion, lies in the fact of moving large quantity of cash in and out of the system is not easy. So really, Bitcoin as a money laundering tool, yes, for small quantities, it may be possible. You'll get some anonymity with the pseudonymity, but you will not get full anonymity unless you're using a Tor server. Sorry, I have to rush a little bit in this. So there was some attack on Bitcoin. Essentially, they're attacking the wallets, so like Coinbase, or they're including in the blockchain some child pornography. If you want to see more information, you can follow these links. So to me, the Bitcoin security is not fully solved, because software security is partly a human problem. And software security is not solved at this time. I mean, there's always a vulnerability in software that can be found. So the implementation is always, in my opinion, the problem. I don't have time to cover this, but there are other cool use of blockchain technology, like pure digital things, like name mapping or internet name mapping, and they use a name coin. So now you can use a name coin like Bitcoin, but the coin are used just to buy internet name. You can have smart property in trade. I mentioned that, or complex contract like Ethereum. That's really the goal of the cryptocurrency called Ethereum. They can do crowdfunding or initial coin offering. You can do markets and auctions, prediction market, games, and data feeds. There are a lot of cool other applications. So in conclusion, I covered the mechanics of Bitcoin with proof of work. I showed that the cost of running Bitcoin is very high. There are a ton of potential applications for blockchain. Decentralizing systems that usually require human intervention. There are some pros, so efficiency of ownership transfer, greater privacy, but there are new categories of problems like software security in addition to physical security. It's hard, in my opinion, to use as a real money laundering tool or large amount of money laundering tool. Bitcoin security is, we already mentioned that, secure as software running it. It's not solved. The future lies in the fact that Bitcoin will adapt or fork. If not, it will disappear in favor of more efficient, cheaper, more disruptive alternatives. And just to show you some perspective in terms of the transaction speed again, compared to Visa and PayPal, to show that really Bitcoin is one of the least efficient of all. Okay. So with that, thank you very much. I'll have only a few minutes for questions, unfortunately, or maybe only 1 minute. I apologize for that. So please.
Thank you very much, Eric. It was a very interesting and insightful presentation. We have time for one quick question. Please identify yourself if you make the question. I have a quick question, actually. So there are many currencies, cryptocurrencies, like you were pointing out, Bitcoin, Ethereum, and some others. What are basically the basic differences among them? The technology, underlying technology is the same, but
no, they can use a difference. The consensus may be obtained in a different way. So you can have proof of stake instead of proof of work, for example. Okay. But typically their goal or their specialty, they usually focus on something. Like Ethereum is really focused on executing smart contracts, or Namecoin is really focused on only managing namespace, right? So they name internet names. So they all have their specialties, and most of them they are a fork of Bitcoin, like Bitcoin Cash, for example. And I think I'm pretty sure Namecoin is also a fork from Bitcoin. So many of them are a fork from Bitcoin, but they may be completely different and run completely differently. If I remember correctly, for example, Ripple, I don't think it's decentralized at all. I think it's centralized. Like for a company, for a bank, for example, they may not have any reason to decentralize. Right? They just want a blockchain, which is a ledger that allows the different systems in their company to interact with each other, and blockchain very elegant way to do that.